talking about atomic structures. We're going to be looking at kind of the atom and the three subparticles, which are protons, neutrons, and electrons, and kind of how do they make up the properties of an atom. So first, what are atoms? As we all know, we've all been familiar with this definition. Atoms are the smallest piece of matter that has a chemical property of an element. Basically meaning that atoms are kind of the smallest piece that we cannot create nor destroy, and it exists, and it's kind of the smallest thing that we can actually see that is made of matter. An atom is made of three subparticles. First, we have the proton. As you know, and if you don't know this already, the proton is inside the nucleus of the atom. It has a mass of what we call 1 AMU. AMU, by the way, is a unit that was invented in chemistry. It's kind of a unit that we came up with to talk about very, very small. So obviously, as you know, an atom is the smallest piece of matter. Then the proton is even smaller than the atom. So we needed a unit that can kind of correspond to that. So instead of saying 1.67 times 10 to the negative 27 kilograms, we refer to that as 1 AMU. And as you all know, the proton is a positive charge. Then we have a neutron. A neutron also lives in the nucleus, okay? It's also located in the center. Protons and neutrons are actually kind of clustered in the center of the nucleus. It's the center of the atom. A neutron, as well as a proton, has the same mass. It has a mass of about 1 AMU, or 1.67 times 10 to the negative 27 kilograms. That means super, super, super small. And a neutron, unlike a proton, though, has no charge at all. So the charge is 0. Last but not least, we have an electron. An electron does not live inside the nucleus. An electron actually floats outside the nucleus in what we call the cloud. A lot of us refer to it as different names, but I call it the cloud. And an electron, if you thought a proton and neutron were small, an electron is tiny, super tiny compared to a proton and a neutron. An electron actually has a mass of 0.00055 AMU, or in kilograms, 9.10 times 10 to the negative 31 kilograms. So it's way smaller than a proton and neutron. However, compared to a proton and neutron, an electron actually has a charge of -1. And like I said, 1 AMU is kind of the mass unit, atomic mass unit that we refer to it. It's a unit that we came up with in chemistry kind of to talk about very, very small particles that you really can't see. Now, what gives an atom its identity? So basically, what gives you your identity, if we talk about humans, it kind of, you stand out from someone else because, let's say, your eyes or your hair or your eye color or your eye type or your height, or even kind of the special features that you have in your face, like freckles, moles, things like that. But obviously, atoms don't really have a face. They don't really have hands. They don't have feet, things like that. So what makes them different? So what makes, like, let's say, for example, a carbon atom different from an oxygen atom? So every atom has a different number of protons. So every single atom that you see in your periodic table, remember, has a different number of protons. Now, the number of protons kind of determines the unique identity of that atom. So the atomic number shows the number of protons. So that number that I talked to you guys about, if you look at your colored periodic table, the number that's on top of the atomic symbol, or the symbol of the atom, that is what we call the number of protons, or that's what we call the atomic number. So the atomic number is equal to the number of protons. This is a very, very key, I would say, a formula that you need to remember. You're going to have it on your quiz, so make sure you put a star around it. Now, the nucleus and the mass. So as I told you guys before, the protons and the neutrons kind of live in the middle of the nucleus, and each one has the same mass. So each mass of each proton and neutron has about 1 AMU. Now, the mass of the nucleus is the number of protons and neutrons. So basically in AMU, if we were to talk about how heavy an atom is, we would add the protons and the neutrons in the nucleus since they have about the same mass. Now, why don't we add the electrons? Because like we said, the protons and neutrons are super small, and the electrons are even smaller than that. So they really make little to no difference in the mass of an atom. So when we talk about the mass of an atom or the mass number, we usually just add the number of protons plus the number of neutrons. Now charges. So basically, like we said before, protons have a positive charge, electrons have a negative charge. Neutrons have no charge. So if we want to talk about the overall charge of an atom, we usually do protons plus the negative. Since electrons are negative, we multiply a negative times the number of electrons. Or to say it more clearly, the charge of an atom is usually identified by the number of protons minus the electrons. Now, information of an atom or an element. Element symbol. Sometimes element symbols look something like this. Now you might think, I've never seen an element symbol look like this. Well, just so you know, this is kind of a generic one. An element symbol is kind of the letter in the middle. And remember, that's what I told you guys. Sometimes it's one letter, sometimes it's two letters. If it's two letters, it's always one capital and one lowercase. Then you will if you ever see an element like this, that C represents the charge. Sometimes the charge will be present in an element symbol, sometimes it won't be. In this case, in our periodic table, it's not. This is how many atoms we have of that element. Remember how I said before, if we have subparticle 2, usually means that we have 2 elements of that. If we have a 3 there, like when we talked about diatomic elements, if we have a 2 there, that means we have 2 of that atom. Now, the atomic number, if we have a symbol like this, the atomic number will be located at the bottom left-hand corner. And last but not least, the mass number would be located in the top left-hand corner. So, for example, oxygen, sometimes you might see something like this. Oxygen, like we said, the charge is at the top right-hand corner. That's the -2. Oh, sorry. First of all, we talk about the element symbol. That's oxygen. Then the charge is -2. Then on the bottom bottom right-hand corner, we don't have any number there. That means that if we don't have a number there, that means that we only have one of that atom. Then we have an 8. The 8 stands for the atomic number, that number that you see at the top of the symbol in the periodic table. Then finally, we have the mass number on the top right-hand corner. This number, top left-hand corner, my bad. And this number you won't find in the periodic table because this is the mass number. This is the mass for one isotope, okay? And we'll talk about isotopes in just a second. All right, so if this is the let's practice, we're going to use the 3 equations that we just saw previously, which is atomic number equals the number of protons, mass number equals protons plus the number of neutrons, and charge is equal to protons minus electrons. Again, we are filling in the missing values. So you are going to have something like this on the quiz where you have to fill in the missing values here. And you're going to be able to do this with your periodic table and with these 3 formulas. So first of all, let's look at magnesium. They told us our element. And guys, when they tell us our element, that means that we can look on here and we can find the atomic number up here. Even if, as you guys can see, they don't give us an atomic number. However, they give us the name. So we know we're using magnesium. So for atomic number, we're going to put in 12. Okay? Now, if we know the atomic number, like we said before, we know the number of protons. So the number of protons is also 12, okay? Now, if we know protons, we know atomic number, and if we know mass number, right here, we know protons, we can figure out the neutrons by basically a simple algebra equation. So if we have 25 as the mass number with 12 plus neutrons, we can figure out neutrons right here. Okay, again, subtract 12, subtract 12. This is an easy math. 13 equals the number of neutrons. Okay, now for the charge, okay, we have protons minus electrons. So we have the charge, again, plus 2. We have the protons, which is 12. We don't know the number of electrons, but again, a simple algebraic equation we can solve for E. Minus 12 minus 12, 2 minus 12 gives us -10 equals -E. However, as you know, we can't solve for a variable, so we just divide both sides by -1. -10 divided by -1 gives us 10 is equal to E, so 10 electrons. Okay, the symbol, and I forgot to do that, the symbol for magnesium is Mg, and you just have to put Mg. All right, and that's it. For the bottom one, atomic number is 82. Okay, so that means that I just have to quickly look over here for number 82, which is Pb, which is lead. So I know my symbol already, Pb, I know my name, it's lead, and my atomic number is 82. Now, if my atomic number is 82, remember, atomic number equals the number of protons. So if this is 82, this also has to be 82, right? And now, if I'm looking for my mass number, I simply add the number of protons plus the number of neutrons. And that's a little bit of, in order for you to be accurate, you can do it by hand, or you can also use your calculator. So it's 82 plus 126 gives us 208 for the mass number. Okay, and then the charge, again, we're going to do protons minus electrons. So we have 82 protons minus 82 electrons, and obviously we know that is 0. So what are isotopes? Isotopes are atoms of the same element with a different number of neutrons. So if you guys remember, I told you isotopes are kind of like every atom has siblings that look exactly like it. However, they are differentiated by a couple of things. And so you also know some isotopes are radioactive, which means they are dangerous. They can cause mutations if exposed to humans and other kind of like cancers and other kind of complications. But most of our isotopes, especially on Earth, are quite stable. That's why it's a very livable environment. So let me give you an example. We have hydrogen 1 and hydrogen 2. In the difference basically between them is that hydrogen 1 doesn't have a neutron, but hydrogen 2 does. So hydrogen has a mass of 2 and hydrogen 1 has a mass of obviously 1 because it doesn't have a neutron and all it has is a proton. So isotopes basically mean that they have the same number of protons. The neutrons, again, is the number that differentiates between them. So they are still the same element. They are what we call sister elements. The only difference is that hydrogen 1 does not have a neutron, hydrogen 2 does have a neutron. And that differentiates their mass. So, how can we differentiate isotopes, or how do we know when we're talking about a single isotope? Let me give you an example. Sometimes the mass number at the top will be 12 and 13. As you can see, carbon 12 has one less neutron than carbon 13, and carbon 13 again has one more neutron. Other ways that we can also do this is by identifying it after their name. So carbon 12 again has one less neutron than carbon 13. So mass number versus atomic mass. So remember how this is what I was talking about in your periodic table. So a mass number is just simply what we've been doing, which is the number of protons plus the number of neutrons. So what we've been doing is we've been actually calculating the mass of one specific isotope. However, what you have in your periodic table, it says down here, is found in the periodic table, is you have the average atomic mass, because this averages the actual masses of all the weighted isotopes. So all the isotopes, this is not a whole number since we're taking an average. Usually averages are not whole numbers. Mass number, on the other hand, is always a whole number because there's no element that has half a proton that has half a neutron or 1/3 of a neutron or 1/4 of a neutron. We always have a whole neutron and a whole proton. Okay, and this number will never be found in the periodic table. So how do we calculate the average atomic mass of an isotope, of isotopes altogether? So basically, when we want to take the weighted average, normally when we talk about averages, we always talk about add them all together and divide by how many you have. This is a little bit different. This is not exactly the same. So the average atomic mass of a single atom regarding the isotopes is we take the sum of the abundance of the isotope. So how often is it found on Earth? So we always take that into consideration, and we multiply that times the mass of the isotope. Okay, so we do this for every single isotope. So let's say there's 4 isotopes. We take the abundance of that isotopes times the mass, then the abundance of the second isotopes times the mass, and then the abundance of a third isotopes times the mass, the abundance of the fourth isotope times the mass. We add them all together. This is why you have this little e, backwards e, that's what it means. It means the sum of. All right, so when you have this problem, something like find the atomic mass of chlorine if chlorine 35 has a mass of 34.969 AMU And chlorine 37 has a mass of 36.966 AMU and is present 24.22% of the time. So basically, what you want for every single isotope is you need an abundance so you can multiply it times the mass. So if we were to make a little table, for example, chlorine 35, its abundance, we don't know because they're not telling us the abundance here. Okay? But we do know its mass, and the mass of chlorine 35 is 34.969. As you can see, the 35 just stands for kind of the rounded up of the mass. For chlorine 37, we do have an abundance. The abundance is 24.22% of the time. And we do also have a mass. We have 36.966. Now, how would we solve for this then? Well, an abundance, guys, normally the abundance of all the isotopes has to add up to 100. Again, the abundance of all the isotopes has to add up to 100. So you can figure out the abundance of chlorine 35 by simply subtracting 24.22 from 100. So you do 100 minus 24.22, and you guys get 75.78%. So now you have your table filled out. Okay, so that's the first step there. Now, there is before you multiply, as you guys know, like let's say, for example, we say a shirt is 20% off. You don't multiply or you don't subtract the price of the shirt minus the 20%. What you actually do is you actually have to turn percentages into what we call decimals. How do you turn them into decimals? You divide each one by 100. So the abundance of 75.78, we first have to divide by 100 in order to get it into a decimal. So I have it here already, so I'm just going to divide this by 100, and that's the decimal I want. So it would be 0.7578 multiplied by the mass, which is 34.969. And again, I added plus because remember, we're going to add all of these up. That's what this little e is for, is adding up all your isotopes. And then we're going to do the same thing with 24.22. We're going to divide it by 100 to get it into a decimal. And we have 0.2422. And we're going to multiply that by its mass, which is 36.966. Okay, so always do like we're going to follow PEMDAS, so we're going to do what's inside the parentheses first. So we're going to do 0.7578 times 34.969, and we're going to get something, a pretty big number. So just write the number for now, and then we're going to round till the end to the correct number of sig figs. 26.4995082 plus, and we have 0.2422 times 36.966, and then that gives us 8.9531652, and we're going to add that to 26.4995082, and that's going to give us 35.45. The reason why we want 4 is because 24.22 has only 4 sig figs, so we're only going to round to 4. The 2 doesn't make the 5 round anywhere, and we have 35.45 AMU. Now, how do we know this is correct? And you can always check your answers for these. So we're looking for chlorine. Chlorine is number 17 in the periodic table. What is the average atomic mass for chlorine here? 35.45. What did we get? 35.45. So I know this is my correct answer.